Let's look at how the first continents formed after the Big Bang, how they collided to form today's landmass, and how we will have another supercontinent in only 200 million years. Formed around 3 billion years ago, it was called Columbia by its discoverer, but others prefer the name Nuna. This ancient continent was entirely surrounded by ocean and assembled like a jigsaw puzzle from pieces that were created as early as 4 billion years ago. These fragments, known as cratons, were initially separated by large gaps. However, over hundreds of millions of years, these gaps closed and the continents merged. Although the exact number of fragments that came together to form Columbia is unknown, scientists estimate it was somewhere between 30 and 60. After Columbia, our next supercontinent was Rodinia. It began assembling around 1.1 billion years ago, likely starting with the collision of 3 smaller nuclei. By 900 million years ago, most of Rodinia had taken shape, although some areas such as Antarctica still had far more mountain building to go through. At its greatest extent, the supercontinent was 180 degrees opposite the equator. With no major mountain chains or wide valleys, Rodinia looked much different than the Earth we live on today. Instead of a jigsaw puzzle of fitting pieces, it was more like a pile of Legos thrown into a box. Around 750 million years ago, the breakup of Rodinia began. As the supercontinent split apart, many smaller continents were born, including what would eventually become part of North America, Europe, Asia, and Africa. But not everyone agrees that Rodinia broke up quite so cleanly. Some researchers suggest that the older parts of the supercontinent, such as the Baltic and São Francisco cratons, were largely unaffected, while the younger parts, such as the Congo and Kalahari cratons, were reworked and dispersed by intense volcanic activity. And this volcanic activity is one reason why there are so few fossils from this period of time. The other reason is that the majority of Earth was still underwater, which made it difficult for organisms to survive, let alone be preserved in the fossil record. One notable feature of this era was the formation of glaciers near the South Pole, leading to a snowball Earth event. During this time, the entire planet froze over, leaving behind deposits of glacial till now found in places like Wyoming and Utah. Evidence suggests that melting ice released vast amounts of fresh water into the ocean, disrupting ocean currents and causing significant climatic shifts. In fact, the release of meltwater is thought to have played a role in the mass extinction that marked the end of the Ediacaran period. During this time, life began to change from single-cell to multi-cell organisms. Even though the fossils are rare, one notable exception is the Burgess Shale in Canada, which contains an abundance of fossils from the period. There are also numerous examples of trace fossils, which are evidence of an animal's activity, such as burrows, tracks, and even feces. All this evidence paints a picture of an Earth that was changing rapidly. While the exact timing and mechanisms of these events are still debated, it's clear that the Snowball Earth event was a significant turning point in the planet's history. It shaped not only the physical landscape, but also set the stage for the explosion of life that would occur in the following eras. In the previous video, we talked about the collision of Rodinia and the formation of new continents. But when we left off, there was still a massive amount of mountain building yet to take place. So let's pick up where we left off and see how the world changed during this period. First off, we need to talk about the Grenville orogeny, which took place between 1200 and 940 million years ago. This mountain building event was caused by the collision of Laurentia, which is the ancestral North America, and Baltica, which is the ancestral Europe. As these two continents collided, they formed a gigantic mountain range known as the Grenville Mountains. These mountains were so tall that they dwarfed even the Himalayas. But unlike the Himalayas, the Grenville Mountains didn't stop there. They extended all the way around the globe, forming a continuous belt of mountains that encircled the supercontinent of Rodinia. But this wasn't the only mountain building event that took place during this time period. Between 900 and 540 million years ago, the Pan-African orogeny created mountain ranges that stretched from Newfoundland to South Africa. These mountain ranges were the result of the final assembly of Rodinia. As the supercontinent came together, the crust was heated up and pushed upwards, creating massive mountain chains. But as the collisions continued, these mountains were eventually worn down and eroded away. So what happened to the remnants of these once mighty mountain ranges? Well, some became part of the stable cratons that we see today. For example, The Barberton and Zimbabwe cratons in southern Africa contain rocks that date back to the formation of Rodinia itself. Other fragments were lost forever as they were consumed by the growing ocean basins. Over millions of years, these fragments became part of the mantle, the layer of Earth between the crust and the core. As we talked about in the last video, around 550 million years ago, the breakup of Rodinia began. As the supercontinent split apart, many smaller continents were born, including what would eventually become part of North America, Europe, Asia, and Africa. However, the journey of these continents was just beginning. They would collide and combine in various ways over the next several 100 million years, eventually forming the supercontinent of Pangaea around 335 million years ago. The exact path that led to the formation of Pangaea is still debated among geologists, but we know that the continents involved include Laurentia, Baltica, Siberia, China, India, the Antarctic Peninsula, and Australia. One theory proposes that the assembly of Pangaea began with the collision of Baltica and Laurentia, forming the nucleus of the future supercontinent. Other smaller continental fragments then accreted to this nucleus, eventually forming Pangaea. However, Pangaea would not last forever. Around 175 million years ago, it began to break apart, giving rise to the supercontinent we live on today. But this process was slow and gradual, taking tens of millions of years to complete. As the continents drifted apart, new ocean basins formed and the Atlantic Ocean began to widen. During this time period, the climate of Earth was much different than it is today. The interior of the supercontinent was likely dry and desert-like due to the lack of moisture. As the continents began to drift apart, this changed and the climate became more varied, allowing for the formation of new ecosystems and the evolution of new species. Pangaea is also known as the age of the dinosaurs. This group of reptiles dominated the land masses during this time period. They came in all shapes and sizes and were well adapted to their environment. The Jurassic period saw the rise of the sauropods, the largest of the dinosaur species. These included the famous Diplodocus and Brachiosaurus. But not all dinosaurs were so enormous. The velociraptor, a small agile hunter, was also popular during this time. During the Cretaceous period, flowering plants appeared and quickly diversified, becoming an important part of the ecosystem. The climate at this time was generally warm and humid, which allowed for the growth of lush vegetation. This provided plenty of food for the dinosaurs and other animals, leading to an explosion of biodiversity. But this age of giants would come to an end with the mass extinction that marked the end of the Cretaceous period. This event is often referred to as the Cretaceous-Paleogene or KPG extinction event. It is believed to have been caused by the impact of a large asteroid or comet, which caused widespread devastation and triggered a chain reaction of events that led to the extinction of many species, including the dinosaurs. So where do we go from here? What will the Earth look like in 200 million years? Based on current trends in plate tectonics, scientists predict that most of the existing continents will continue to move towards each other and collide again. This process has already begun with the formation of the Eurasian and African plates. As these plates continue to converge, they will eventually merge to form a new supercontinent. Some researchers believe that this new supercontinent will resemble the ancient supercontinent Pangaea, which formed around 335 million years ago. Others propose that the new supercontinent will be similar to Rodinia, which existed around 1 billion years ago. However, there is also speculation that the configuration of the new supercontinent will be unique and different from any that have existed before. Regardless of its exact configuration, scientists agree that the formation of this new supercontinent will have profound implications for the planet as a whole. The collision of continents can cause massive mountain-building events, volcanic activity, and changes in sea level. These events can have far-reaching consequences for the climate and the distribution of life on Earth. What's more, the formation of the new supercontinent is expected to trigger a mass extinction event. As the continents collide, many species will be wiped out as habitats are destroyed and ecosystems are disrupted. However, this will also create new opportunities for the survivors. The mass extinction that occurred at the end of the Cretaceous period, for example, is believed to have paved the way for the rise of mammals. Similarly, the formation of a new supercontinent in the distant future could lead to the emergence of new dominant species. In short, The formation of a new supercontinent is a monumental event that will reshape the planet in ways that we can only begin to imagine. While we may never see it for ourselves, the evidence left behind by our ancestors suggests that such events are a normal part of Earth's history. As the continents continue to move and evolve, we can be sure that our planet will continue to change in ways that are both dramatic and awe-inspiring. Thanks for watching, and I'll see you in the next video.